But now that we have done this, let us go back. We need to do one more thing.
Okay.
Related to the system. So we know that you are doing something inside these transmitter and receiver blocks, modulation, demodulation, etc. But now let's come to this antenna.
Yeah.
Right?
Yes.
We should not forget because that's what we started with, and that was the key concept.
Correct.
In this, that was the key thing that allowed us to convert the electrical signal to an electromagnetic signal.
Right.
And we talked about the plane wave, etc.
Yeah.
So there are a few things we need to know, right? So the first thing we need to know is, from physics theory, I'll just, point out a few things.
Okay.
If you choose, so let's go back to this EM wave.
Yeah.
Right? We said C equals F lambda.
Yeah.
Now we are now choosing F, and corresponding to that, there is the lambda is automatically chosen.
Fixed. Yes.
Right? This is, so you think of lambda as C over F.
Exactly.
F is chosen for communication.
Yes. So for FM, it's some 100 megahertz.
Exactly.
Let's say. Right. And AM, like you said, is at most 1 megahertz.
Correct.
Correct?
Correct.
Right.
So you choose the frequency.
Yeah.
Or a frequency band for wireless communication. Automatically lambda is chosen.
Yes.
Now it turns out that depending on what you choose for F, there are certain physical limitations. So one of the things you would have seen is that if you let us see, if you were to look at Wi-Fi, right, as you move further and further away from the wireless router, your signal keeps getting weaker, your information, speed, bandwidth keeps dropping. That is because fundamentally the minute you radiate out, right, that is, normally these antennas are all radiating out in all directions. Right? And especially things like AM radio and FM radio, you are trying to, it's a broadcast communication.
It's a broadcast.
You are just radiating out so that everybody
every
gets
direction.
In every direction. Right? That's the number one thing. Majority of terrestrial communication on Earth is like this.
Right.
Now, some of them rely on properties of the atmosphere.
Okay.
You rely on reflection from certain portions of the atmosphere. For radio, for example, it could be from the ionosphere.
Okay.
Some, ways of remote sensing uses scattering from the troposphere.
Okay.
And so on.
Okay.
Right. So we don't need to worry about that for the electronic side.
Yeah.
But one thing we need to keep in mind is that depending on the choice of the frequency, you may, or so imagine you're trying to communicate. And the user is standing here. Right. And there is actually a tall building here. Okay, this is a building. Now, if you have a low frequency signal, it turns out that there are two things that work in favor. One of them is that it is actually able to penetrate because there is some electromagnetic property called skin depth. It is able to penetrate.
Okay.
And the amazing thing, because it's a wave, it is also able to bend, which is based on diffraction.
Right.
So, if the frequency is low, the wave nature is very prominent because the wavelength is very large compared to the dimensions. It is able to penetrate as well as go around.
So can we take two examples here, like FM and AM?
Sure,
you said,
absolutely.
100 megahertz and 1 megahertz.
Absolutely. So let us
what
say
does the lambda look like?
AM is, let us say 1 megahertz. And we'll say FM is 100 megahertz.
So what are the corresponding?
Let us calculate the lambdas. So AM lambda is basically 3 into 10 power 8 by 1 into 10 power 6. Which is basically 300 meters.
Which is about 300 meters.
Okay. As you can see, it's a very wide wavelength.
Very
easily it will bend around buildings. There is no problem at all. Because any small structures, the wave is able to bend around.
Wow.
Okay. And if you look at FM lambda, it's not that different. It's still, so
by 100 10 power 8.
By 100 megahertz is what we took, 1 into 10 power 8, which is still 3 meters. Now, it is able to bend around structures which are large. 3 meters is still large. It is also able to penetrate. It turns out that the skin depth is also very high.
Yeah.
So FM radio also you can receive. You may receive a smaller signal, but you can still receive very comfortably.
Very comfortably, beyond the building and all that.
Beyond the
buildings
building.
are not obstacles.
Absolutely. Now, now you can see these calculations. If you choose 100 megahertz, it is giving you 3 meters. Now you see, if you go to
2.4 gigahertz.
2.4 gigahertz, exactly.
Right.
So Wi-Fi.
Wi-Fi.
Frequency 2.4 gigahertz.
Yeah.
The lambda is basically 3 into 10 power 8 by 2.4.
But why don't we just say 3 gigahertz?
Yeah, sure.
Does it
Let's just say
really
3.
matter? Yeah.
Well, okay. So what I will say is, I'll just say this is approximately 0.1 meters.
Correct.
Okay. So this is approximately 3 gigahertz.
Yeah. 0.1 meters.
0.1 meters. 100 centimeters. Okay.
Yeah.
So what you will find, it is able to bend around small obstacles, but the minute you go 2 rooms away, it's gone. It's neither able to penetrate very well. It's also not able to bend enough.
Wow.
If you go around 2 walls away or 2 structures away, it is hard, and you will find this.
So that's why the FM radio station, though it is kilometers away, you're still able to receive it, but your Wi-Fi 2 rooms away, you cannot receive it.
Absolutely.
Right.
So in fact, there are 2 parameters that decide whether you are able to receive or not. One of them is this ability to bend, penetrate, etc. The other thing is the power that is sent out from the transmitter.
Correct.
Because remember, you are isotropically radiating in all directions.
Yes.
The power you receive in any one direction is basically the area of a
ratio
sphere,
of the area,
ratio of the overall sphere versus what the actual area you are of the antenna itself.
Yes.
Okay? But that is an advanced concept which I think students will learn.
We will not get into
We will not get into that.
Okay.
So now you can see the reason for miniaturization of electronics for wireless, for cellular phones, etc., is because you are transmitting and receiving at higher and higher frequencies. The antenna structures, one of the questions you are asking me, why does your cell phone not have a long antenna compared to your radio?
Correct.
It is primarily because the size of the antenna is directly related to lambda.
Okay.
So your size of the antenna is a function of lambda.
Yeah.
It will typically be maybe half the, it's of course an area and not a size, but it's a function of lambda. It will be like, maybe half lambda by half lambda or something like that.
Okay.
Look like that.
So you can compactly accommodate it in that small package.
Exactly.
Right?
Exactly.
Okay, beautiful. Right. Okay, that's very nice. I think we have covered the theory in reasonable detail. So the primary takeaways is just elementary trigonometry.
Yes.
Governs amplitude modulation, first of all, right?
Correct.
There is nothing fundamentally limiting in terms of power or something, right?
Absolutely.
The modulation is not for the sake of power.
Yes.
Right? It is basically to keep your signals orthogonal to each other.
That's correct.
And not allow them to mix and get garbled. Okay? And that orthogonality is what we showed with the multiplication.
With the multiplication and integrating.
Correct? And integrating, right?
That's right.
Okay. And of course, FM, you showed some FM signal, but demodulation is slightly more complex.
Slightly more complicated. So we will not deal with that.
We will not deal with that now. Okay, great. So, so why don't we now come back to that experiment, right?
Yes.
Because one is, so there were 2 things in this process of transmission reception. One was, okay, you had to make the signals orthogonal and allow them to go through free space. That is what we did in theory. The other is the actual transmission and reception of the antenna.
Absolutely.
So I see you have some experimental setup here.
Yes.
Right. So
I'm sure the students must have seen this and must be wondering what's going on.
Yeah, exactly. So
right?
Can you maybe just explain what this setup is first, and
Absolutely.
then we'll do the experiment.
Absolutely. So what we have done is we have basically taken our kit, which has the oscilloscope and the signal generator.
Yeah.
And we want to, so that stands in for the transmitter and the receiver.
Okay.
So this is basically what we have done. We have set it up such that this is the signal generator.
Yeah.
Oh, signal generator.
Yeah.
And this is your oscilloscope.
Yes.
So that is standing in for these 2. Now we need to create an antenna.
Okay.
Now designing an antenna is not trivial.
Yeah.
But what you can do, it turns out that there are basically you can create what looks like an antenna.
Okay.
It is not very efficient.
Yeah.
But for proof of concept, it's good enough.
Right.
And turns out there are antennas called loop antennas.
Loop antennas.
Right. And we are going to use that.
Okay.
And we are going to do the same thing here at the receiver.
Loop antennas. Okay.
And we are going to use a combination of the signal generator plus the loop antenna as the transmitter, and the oscilloscope plus the loop antenna as the receiver. And a loop antenna is simply a metallic wire bent in the form of a loop.
Okay. So you just take a wire and just coil it.
Just coil it.
Okay.
Now, if you coil it many times, you will also get an inductor.
Ah, okay.
Okay. And in fact, an antenna can have an inductance as well.
Yes.
Right. But we are trying to separate out. We are trying to convert. Oh, and by the way, one of the things I said is sending information. You can send it through light, wireless through a carrier, and so on. Turns out many students might have heard of NFC on their phone.
Okay.
Near field communication.
Okay.
It is primarily inductive based. When you take something very close, you actually create a coupling between two inductors.
Okay.
You can send information wirelessly through that as well.
Okay.
Right.
Great.
So I think what we are trying to demonstrate here is we are trying to primarily create, instead of winding as an inductor, we are trying to wind it as a loop antenna. That's what we are trying to do.
Okay. Great.
Right? And this is and it can be experimented at various levels of sophistication.
Okay.
Right. The one that we are trying to show is only going to be a very basic one.
Right.
And one more thing to keep in mind is related to the calculations that we just did.
Yeah.
So as you can see, the wavelength. So our discovery kit that we are using right now has a limitation of about 25 megahertz.
Yeah.
So 25 megahertz corresponds to about 1/4 of the frequencies, 12 meters.
12 meters.
Right?
Yeah.
So the typical antenna, as we saw, the antenna size is the function of lambda. So if you want to send a 25 megahertz, you need a 12-meter long antenna or something similar to that. Which is why we are building a very, very basic system.
Yeah.
But it's good enough to demonstrate the concept.
Okay. Great.
Right. So what we have here is basically two sets of wires.
Yeah.
A yellow wire and a blue wire.
Okay.
So standing in.
Okay,
that's right.
So I'm going to now put these two up.
Yes.
Right. So you can see that the two wires have been looped around. Right. So okay. And which one is connected to the oscilloscope?
Okay. So I believe so. Channel 1 is the function generator.
Blue.
The blue one. Perfect.
So the blue one is what is going to radiate.
Is going to radiate.
Right? Or inductively couple. We'll figure that out.
We'll figure that out. Actually, so one thing they need to know to figure out whether it's inductively coupling, etc.
Yeah.
So well, they still don't know what inductive. We have talked about mutual inductance in one lecture.
Yeah.
But we will basically tell them that if you have two inductors, it is you have EM fields associated with them.
Yeah.
And if you have a current passing through them, it will create a time. If you have a time varying current, an AC current, it will create an AC electromagnetic field. You have in the physics, you have the concept of field lines and flux.
Yeah.
And it is possible for you to have linkage between these two.
Yeah.
Okay.
Right.
Which is called some coupling factor, let's call it K or something.
Okay.
Okay. That is what near field communications exploits.
Yeah.
Okay. So that is something that just a quick introduction to what coupling means.
Yeah.
Okay. Now what we are trying to do is if you place the inductors very close, the coupling will be very strong.
Very strong.
The minute you move them even a few inches away, more than 6-7 inches, the inductive coupling should be very slight.
Low. Okay.
That's what we are hoping.
Okay, great.
Okay. So let us shall we go on to the experiment?
Yes.
So okay, so now actually I have not you can see it is stopped. I am not running anything.
Okay.
Shall we see what the scope is?
So
seeing?
this is okay.
Yeah. So this is nothing. I have turned off. As you can see, I stopped the.
Yes.
There is nothing going from this wave generator, and this is just some kind of noise that it seems to be picking up. Now, you can see. Okay. So if you just lift the receiver,
the
you
yellow
can see
cable.
it seems to be picking up something intermittent.
So approximately what frequency is that?
Well, this is 0.5 microseconds, and you seem to have maybe 10 periods.
Yeah, 10 periods.
So that's about, it's about 0.05 microseconds. So let's do a quick back of the envelope calculation.
Yeah.
So we are basically seeing, so this is the pickup, right?
Yeah.
So the antenna, we are not sending anything, but it seems to be picking up something whose time period is about, let's say 1/10 of 0.5 microseconds.
Yeah.
0.05 microseconds. This is about 50 nanoseconds.
Yeah.
This is about 50 nanoseconds.
Correct.
Which means the frequency is 1 over t, which is about 2 gigahertz.
2 gigahertz.
Okay.
Okay.
In fact, there is a whole bunch of stuff that is happening.
Is this 2 gigahertz?
Is this correct?
No, it's 200 megahertz.
Is it? Let me see. It's 200 megahertz. Thank you.
Yeah.
Because in fact, it's 20 megahertz, isn't
20
it?
megahertz.
It's
Exactly.
20 megahertz. Thank you.
Yeah.
Because 50 nanoseconds. You're absolutely
Exactly.
right.
20
You're
megahertz.
absolutely right.
Correct. That makes
So
sense.
because absolutely. This is right. 0.5 microseconds, about 10 periods. That's absolutely right.
Okay.
So so this is about 20 megahertz.
It is picking up something.
It is picking up something.
And
in fact, the electromagnetic spectrum, frequency spectrum is very tightly packed, especially at these frequencies. You have commercial, you have defense, you have space, you also have some open industrial, scientific and medical bands. So it is very tightly packed
likely
space.
that somebody is transmitting something that we are just picking up.
Absolutely.
But we don't know what it is.
We don't know what it is.
Okay, cool.
Absolutely. Correct.
Okay.
So 50 nanosecond is indeed 20 megahertz.
Yeah.
That's absolutely right. So we seem to be picking up something. Okay?
So I think the point you're trying to make is there is some background noise that is being picked up by this loop antenna at around 10 to 20 megahertz.
At around 10 to 20 megahertz.
Yeah, because we didn't make that calculation exactly.
Correct. And it seems to be intermittent as well, because
Yeah,
if you pick this up, you can see that it is going on and off.
Yeah.
And there are various things related to this. So it could even be your body picking up some part of it, and
exactly.
The orientation matters and so on.
Correct.
Okay.
So now why don't you go and
why don't we go up? Shall we start with something very small, very low frequency?
Yeah.
Maybe 100 kilohertz.
Maybe 10
Maybe
kilohertz.
Should we go even lower?
10 kilohertz.
So let's say 10 kilohertz. So I'm going to transmit a 10 kilohertz signal.
And what is the voltage that you are transmitting?
It's about 2 volts amplitude.
Okay.
So, and by the way, I also want to tell people, you are now radiating outside in free space. There may be somebody using this 10 kilohertz, whatever we are experimenting. You have to be careful. Don't make your antenna too efficient. Because you will interfere with the other. Don't use a commercial antenna.
Yeah.
That much we can tell you.
Yeah.
Don't use amplitudes too large. Right?
Okay. Yeah.
Because you will indeed interfere with whoever is using it.
Okay. Right.
So let me start this. So it is basically sending out a 2 volt amplitude sinusoid.
Yeah.
So let's look at the scope. It's still picking up just some random junk. Now, as you okay, there you go.
Something.
It is picking up something. But not, it seems to be very small.
Yeah.
So let us see.
So just
for
make
10
a note.
kilohertz, I'll just make a note. So first we'll do this a table.
Yes.
Right. So we'll say frequency.
Yeah.
And we'll say the amplitude.
Received amplitude.
Received
RX
amplitude.
Yeah.
Okay. So we said 10 kilohertz. We are really not picking up anything super significant.
Yeah. Noise.
Right. Just noise.
Background noise. Yeah. Correct.
We'll just say it's noisy.
Yeah.
Now, we are not picking up anything. We also need to see, we'll come back. Maybe we'll do the experiment and then come back and analyze. Right. So maybe we'll do it that way. Let me go to the wave gen, and shall we go to 100 kilohertz?
Yeah.
Next.
100 kilohertz.
So 100 kilohertz, and let me stop and run. Okay. And this is just the background noise
again. There is nothing much.
Right.
Okay.
So it's about the same.
Yeah.
So 100 kilohertz. So it's the same.
Yeah.
Then now I'm going to go to
1 megahertz.
1 megahertz. And let me run this. Okay. Okay. Already I see Yes. So let me change the scale. So this is the y-axis and the x-axis. So this is 500 nanoseconds per division. Let me do this because we are at a 1 megahertz.
Yeah.
So you can see the period is exactly 1 megahertz.
Yeah.
Right.
Now, exactly. So it's interesting, right? So what I'm doing is I'm bringing the transmitter and receiver closer and closer.
This is inductive coupling. So let me, okay. So you can see that when you bring it closer.
Yeah.
So let us say 1 volt per division, and I'll also make this 1 volt per, well, this can be 500 millivolts per division. Oh, let's say 100 millivolt per division.
Yeah. Right. So I brought it really close.
This is purely inductive coupling.
Yeah. Right. And then I take it far away.
Yes.
And then it's gone.
And then it's gone. So let me make that maybe 20 millivolts. Yeah. Okay.
See that?
Yes.
Okay.
So maybe if you take it really far away, maybe I'll hold this.
Yeah.
And you extend your right hand, you will see that at some point of time you will be able to see some
saturation. But maybe we need to go to a higher frequency.
To a higher frequency to see that. Absolutely.
Okay. Yeah. Okay, great.
But clearly inductive coupling is strong.
Is strong
when they are very close.
Right? Yeah.
Okay. So let's go back and let's note this down.
Yeah, yeah.
So 1 megahertz. Strong inductive
inductive coupling.
Strong inductive coupling.
Yeah.
Right. So next step is 10 megahertz.
10 megahertz, absolutely.
Okay. So I'll change this to 10 megahertz and same 2 volts.
Okay. Now,
interesting.
These things are kept like this.
So what I'm going to do,
You're changing the axis?
I'm just changing the time axis so that we can see the,
correct.
Right. So shall we say 10 megahertz is 100 nanosecond period.
Yeah.
Right. So this is okay?
Yeah.
Yeah.
Okay. And there I bring it really close, okay, at 10 megahertz.
Yeah,
and
you see a strong inductive coupling as well.
Yeah.
But you can see, even if you go very far away, it's radiating.
Because it's sort of saturating beyond a point.
Exactly.
Right?
Once you go far enough, it is just picking up the radiative element alone.
Yes. Okay. So
interesting. So what I will do, I'll also change this to, I'll go down to about 10 millivolt per division, and you can see.
So you see that as I bring it close, nothing much is happening.
Yes.
But when I come really close,
yes,
you will see the inductive coupling taking over.
Absolutely.
Right. So
correct.
We can say that when it saturates.
Yes. Most likely it is purely radiative.
Yes, exactly. Okay, now can you also go and turn off the signal generator now?
Okay. So let's say I'll stop this.
Yeah.
And you just pick up the background noise.
Again picking up background noise. So there is 10 megahertz signal here already, which is this yellow antenna is picking up.
Absolutely.
But if you turn on that, again, can you turn it on? You see that
can see it's much larger amplitude and it's fixed as well.
Yeah, and I bring it close, you see the inductive coupling sort of kicking in there.
Absolutely.
Right? So this is like reasonable, like what, some 40 millivolt? I don't know.
It's about 20 millivolts.
20
Whereas
millivolts.
that noise that was coming was like, 5
millivolts
or so.
Something.
This is about 4,
so
3-4 times.
Really far away, it is still the same.
It's still 10 millivolts.
Right? So that is the radiation that we are talking about.
Yes. So maybe we'll take a note of this.
Yeah.
So we'll say inductive coupling at close.
Close.
When close.
Yeah.
And radiative when it's far away.
Yeah.
Okay.
Okay.
And shall we also try one experiment at 25 megahertz?
Sure.
So we'll just complete the experiment with 125 megahertz check. So let's run it at 25 megahertz. Okay. As you can see, it's so strong that you're actually able to see, yes, the inductive coupling is extremely strong when you bring them close. And even such far away, the amplitude was almost 30 millivolts.
Exactly.
So it's a better antenna, it's radiating better.
Yeah.
At 25 megahertz.
And also, interestingly, the calculation we made earlier,
Yes.
suggested that the noise was also at 20 megahertz.
Yes,
right?
absolutely.
It was
That's
picking
right.
up signal at 20 megahertz
At 20
already.
megahertz, correct. And
That's what
but
we
you can
got.
see this thing is already a fairly stable coupling at
Correct.
at about plus or minus 10 millivolts.
Yeah.
Right. In fact, what we can do is we can turn off the 25 megahertz and see what it gives. Right. If I were to turn this off, you can see you only get the noise which is like
Only
a few
the
millivolts.
noise. Exactly.
Right. The intermittent noise that you are picking up.
Yeah. And I bring it close, there's nothing.
You won't see anything.
Right.
Absolutely.
So you keep it far away, it's still the same noise, and turn it on again.
Yes.
You can see the radiative component because it's sort of saturated. Thing is,
yes,
this depends on the number of loops. So if I go far away and remove one loop,
yes,
the efficiency changes.
Absolutely.
Right.
So it depends on many things.
Yeah.
So actually, the the field of antennas is a fairly involved field, obviously.
Yeah.
And there are a lot of aspects to antennas.
Yeah.
So, but I think we have done a basic experiment
we
to
have
show.
done a basic experiment to show that the
Right.
wireless. So ideally, if you want to do this experiment properly without any inductive coupling, they should be on two different kits.
Absolutely.
Right. One kit in one end of the room, the other kit on the other end of the room on a different breadboard, absolutely isolated and perfectly. Right.
Absolutely. Absolutely. That's right.
Okay.
So 25 megahertz is also showing something similar.
Yes.
Right. Inductive coupling when close, radiative when further.
Yeah.
So one last thing we can do is to figure out why for 10 kilohertz it's not working.
Yeah.
And actually the reason is very simple, I feel. If you look at the lambda.
Yeah.
For a 1 megahertz signal, the lambda was 300 meters.
Yes.
Right. For a 10 kilohertz signal, it is 100 times that. Right. So lambda is 100 times that is 100 times 300 is 30 kilometers.
30 kilometers.
You have an antenna, the loop antenna is a few meters.
Yeah.
It's not surprising that it's not able to radiate at all.
Exactly.
Okay. And for example, this one is I think I'm right, no? 300 meters for 1 megahertz. This one is 30 kilometers because it's 100. Yeah. This one is 3 kilometers and so on.
Yeah.
Okay. So in fact, even for a 1 megahertz, you can see the lambda was 300 meters. That is why the efficiency will not be much better
very
beyond,
Correct.
will not
exactly.
be very high.
Right. So
right?
So this seems like whatever has been designed, it's about near 20 megahertz.
Near 20 megahertz.
Sort of efficiently
exactly
transmitting and receiving.
Exactly.
Right? Okay. Very good. I think we have demonstrated successfully the process of transmission and reception now, and also isolating the inductive coupling to certain extent.
To certain extent.
Right? We have to be careful there, but yeah. Okay. So I think with that, we are done with the communication part of the discussion in this course. Students will learn a lot more techniques of both analog and digital communication later in their courses, but the fundamentals are very similar to this.
Absolutely.
Thank you.
Thank you.